So yesterday we covered arithmetic operators. Today let's quickly study about the bitwise operators. So bitwise operators are used for long, int, short, char and byte, and they process the bits of the operands. We know bits 0 1 0 1. So they'll process the bits of the operands. So these all are the operators. Some are unary. What do we mean by unary operators? Huh? Yes? Single operand. So we saw the unary arithmetic operators. Likewise, here also you will have a unary operator. So here we have seen all integer types except char are signed integers. Okay, so sign means the value would be plus or minus, but for char the value it is always signed. It is always unsigned. That is, it is always positive. And Java uses 2's complement to represent the integer. So I have talked about in detail what the 2's complement is, how the Java represents any negative number using 2's complement. So higher order bit, it denotes the sign of an integer. Like if it is 1, it will be negative, and if it will be 0, the number would be positive. So in our college, we have already studied about this bitwise logical operators and or not. So let's quickly go through what does it mean. So if we talk about an bitwise operators, everything would be 0 1, right? So one operand, let's suppose one bit is 0 and second operand one bit is 1. Okay, now there will be a different operations on these two bits. There is an operation called OR, A or B. So what does it mean A or B? A or B? So if any operand's bit is 1, so it will result in 1. That's what we call OR operator. And there is AND. What do we mean by AND? Both the bits should be 1, then only the result is 1, else the result is 0. We'll talk in terms of 1 and 0 in case of bits, not false and true. Both the bits are 1, only then the result would be 1, else the result would be 0. Now there is one more operator, XOR. What does it say? XOR operators. If exactly one operand's bit is 1, then the result is 1, else the result is 0. What does it mean? Let's suppose it is like this. The result would be, what would the result? If exactly one operand's bit is 1, then the result is 1, else 0. 1 in this case, in this case, this is XOR operator. And one more operator, this NOT. What's the NOT? What does NOT do? Yes, negates means reverse the sign. If it is 0, it will convert to 1. If it is 1, it will convert to 0. That's the logical operators are. So this NOT operator, it inverts all bits of an operand. So there is a number 5 which is represented as this 0 0 0 0 1 0 1. The NOT of 5 would be this. Okay, please run this code. I have provided all the code here. You can run it, and before running it, please refer to this 2's complement representation. Here also you can find it. Whose complement. Okay, you can study about it. If any doubt, we'll discuss in the class. So NOT operator will reverse the bits. Okay, so if NOT of 5 would become this, so now what will be the sign of this result? Will it be positive or negative? Negative. Why? Huh? Very good. Because highest order bit denotes the sign of an integer. 1 denotes negative, 0 is positive. So when you will run this int a equal to 5, the binary representation would be this. The not will convert it to this. It's a 2's complement representation, right? And its corresponding value in decimal would be minus 6. Minus why? Because the highest order bit is 1. Okay. AND operator, what does it do? It results in 1 if both operands are 1, else it is 0. So let's suppose a is 13, its binary representation would be this. Okay. For b equal to 6, the representation would be this. If we do a and b, what it will give? For 1 0, what would be the result? For AND of 1 and 0, what it will give? In the AND operator, what it will give? Huh? 0, na? What we have studied. AND operator, it results in 1 bit if both operands are 1, else it is 0. So for 1 and 0, it will be 0, 0, 1. Only for 1 and 1, it will be 1. Okay. So the result would be the result bits would be this 0, 0, 0, 0, 0, 1 and 0. If we convert it to the decimal, the result would be 4. Okay. OR operator, it results in 1 if either of the operand is 1, else 0. Okay. And if it is 0 if both the bits are 0. If any one of the operands bit is 1, it will result in 1. If we take the same example, what 1 and 0 will give? 1. 0 and 1? Come on. 1. 1 and 1? 1. Here also 1 and 0, 1. Since both the operands are 0 here, the result is 0. So the decimal representation of this result bit would be 15. So it will result in 15. Okay. XOR operator, what we said, that in the XOR operator, if exactly one operand's bit is 1, then the result is 1, else 0. What it will give? 1 and 0? 1. 0 and 1? 1 and 1? 0. So if we do the XOR operation of these two variables, it will result in this bit, and the decimal representation of these bits is 11. Okay. Now there is another operator called left shift operator. With the name, what does it do? It shifts the bits to the left by a specified number of positions. What do you mean by left shift? What do you mean by left shift? It shifts the bits to the left by a specified number. So each bit is moved to the left and vacant positions on the right are filled with zeros, right? So it is used to multiply an integer by a power of 2. So if each left shift by n positions will multiply the number by 2 की power n. Okay, so let's take this number 0, 0, 0, 0, 1, 0, 1. Let's understand this 0, 0. Okay, so this is the number. When we shift all the bits by 1, what will come in position of this? Which 0 will come? This one, right? Likewise, now what will come in the second? Third one. Likewise here this will come, and here this will come, and here what will come? 1. Very good. Now here 1 will come, here 0, 1, 0, next 1, and in place of 1, 0. Right? So what it will give us? 0, 0, 0, 0, 1, 0, 1. By shifting by one position, 1, 0, 1, 0. How many positions we shifted? 1, 1. Now let's shift another by let's shift by one more position. What will come here? 0, 0, 0, 1, and here 0, 1. We have shifted by 2. What is the decimal representation of this? It is 5, because it is 2 raised to power 0, 1 into 1, and 2 raised to power 2, it is 0, it will not be counted. 2 raised to power 2, it is 4, so 4 plus 1 will become 5, and its binary representation would be 16 plus 4 is equal to 20. So by shifting by, and here its binary decimal representation would be 10. Okay, so by shifting by one position, 5 becomes 10, and by two positions 5 becomes 20. So it means 2 raised to power 2 is 4. By 2 position 5 will become 5 into 2 raised to power 2, which is will be 20. Right? That's what we are saying here. Each left shift each left shift by an n position effectively multiplies the number by 2 raised to power n. Since the n was 2, it multiplied by 4, so 5 becomes 20. In right shift operator, same, it shifts the bits of binary number to the right, and each bit is moved to the right by the specified number of positions, and the vacant positions on the left are filled with the sign bit. What will be the sign bit? What is the sign bit? We have studied na? Sign bit, highest order bit. Highest order bit is the sign bit. Okay, so vacant positions will be filled with the sign bit. If the number is positive, it will be filled with 0, because the sign bit will be 0 for positive, and the sign bit will be 1 for negative. Okay, so right shift operator is used for division by power of 2. Basically each right shift by n, it divides the number by 2 raised to power n. Basically, let's suppose this is a number 20. Here what is the sign bit? What is the sign bit? Highest order na? 0, right? Positive. So if we shift to the right, the vacant position will be filled with 0. So if we shift by 2, so here this one will go here, right? And this one will go here, right? So it will become 0, 0, 0, 0, 1, 0, 1, and all the positions will be filled with 0. So this number 20 will become 5. It means it has been divided by 2 raised to power 2, which is 4. And let's suppose if the number would be negative, so its binary representation would be like this. Here what is the sign bit? What is the sign bit? No, 0, 1. 1 na? Like, this is 1 na? Like, just 2 more minutes, just 2 more minutes. We'll wrap it up. It is 1, right? So when we shift to the right, whatever the vacant positions which will come to the left, what will be there? What will be there? Will fill with, huh? One, na? What we are saying? See, each bit is moved to the right and the vacant positions on the left are filled with the sign bit. Simple. If it is positive number, it will be filled with 0, and if it is a negative number, the sign bit will be 1, so it will be filled with 1. Okay. So here, if we right shift it by 2, the vacant position on the left will be filled with 1, and all these bits will shift to the right. We can test this. Last one is unsigned right shift operator. Why do we use it? Let's suppose we want to shift the bit of a binary number to the right, okay, but we always want to fill the vacant positions with zeros. Whatever is the sign bit, if we always want to fill it with zeros, we will use this unsigned right shift operator with 3. But here in this right shift operator, there were only 2 arrows, but here they are 3. So here what will be done? Regardless of the sign bit, the left vacant position will always be filled with 0. And here also we have a compound assignments like we have seen in the arithmetic operators, like this, equal to and equal to. So what does it mean? And equal to, what does it mean? Huh? Num and equal to num2, it means num equal to num1 and num2, right? We have seen this in arithmetic, right? I plus equal to 2 equal to I plus 2. In the same manner, this means num equal to num and num2. Likewise for all the operators, it means the same. So yeah, this is the code. You can run it on your systems and check.